Charles Hermite, published in 1848, an efficient method for finding the representation of a prime 4k+1 as sum of two squares. His method involved computing a simple continued fraction. You first need to find, through Fermat's little theorem, a n squared plus 1 that is equal to p times k, where n is bigger than 0 but smaller than half the value of p, and then compute a simple continued fraction of n over p, up to the point where the denominator b of its convergence a over v are closest to and less than the square root of p. Then he applied those values to his version of the beautiful formula for p, that is, p equals the square of b times n minus p times a plus b squared. So let's check the case prime 1,299,841, as that will be useful to compare methods. Fermat's little theorem gives us the square 462,779, which will be used in the simple continued fraction. But first, we need to remember that the target denominator is the one that is less than the square root of 1,299,841. That is 1,140. So, computing the simple continued fraction of 462,779 over 1,299,841 give us this list of values. The denominator 1,601 is just above 1,140, so A must be 319 and B 896. Finally, we apply Hermite's version of the beautiful formula, which in fact provides us with a solution. John Brillhart published in 1972 an improvement on Hermite's method, as it demands less computations. You still need to find, through Fermat's little theorem, a n squared plus 1 that is equal to p times k, where n is bigger than 0 and smaller than half the value of p. Then, noting that the continued fraction expansion of p over n, and not n over p as in Hermite's method, has an even number of partial quotients and is palindromic, Brillhart runs the Euclidean algorithm for p over n and finds the solution halfway, before the quotients start to repeat, mirroring themselves. That would certainly happen for the residues r of the Euclidean algorithm closest to and less than the square root of p. As there are 2 times k quotients, starting with p equals a sub 2k plus 1 and n equals a sub 2k, then p is equal to a sub k minus 1 squared plus a sub k squared, which is also equal to r sub k squared plus r sub k plus 1 squared. Here we analyze once again the case prime 1,299,841, and Fermat's little theorem gives us the initial square plus 1 equation. The continued fraction gives us this list of quotients, which in fact is palindromic. Those quotients arise when computing the Euclidean algorithm, and the solution is found before the quotients start to repeat. The values of the squares are those residues after 1,140, that is the square root of p. So the squares for p are 896 and 705. Well, a nice thing to note is that we can extend Brillhart's Euclidean algorithm up to reaching 0 as a residue. And then note that we can couple the divisors with the same quotient, and that the sum of the squares of the divisors is divisible by the prime 1,299,841. See that 462,779 squared plus 1 equals 1,299,841 times 164,762. We can couple the other divisors too, the ones that have the same quotient, in the palindromic sequence of quotients seen before, and check that the sum of the squares of these values is also divisible by the prime. And so we can couple the other divisors until we reach the solution, where 896 square plus 705 square equals 1,299,841. There we have an infinite descent too. The interesting thing is now compare that with a simple descent method. In the simple descent method, the infinite descent is done instead with square plus 1 values, such as 31,507 square plus 1, 1,382 square plus 1, etc. But the quotients are the same, but 1, as in the descent in Brillhart's Euclidean algorithm. 164,762, 6,025, 317, 41, 25, and 2. Furthermore, note below in a simple descent that when multiplying the first and second brackets, those sum of two squares are the same as those in Brillhart's descent. The only difference is 374,283 squared plus 2 squared. In conclusion, both methods exhibit a high degree of similarity when examined in the context of infinite descent. About Hermite's convergence, it's worth mentioning two things. The first one is that while we could derive an infinite descent coupling the divisors in Brillhart's extended Euclidean algorithm, which are the denominators of Hermite's convergence, there's also an infinite descent coupling the numerators of Hermite's convergence, which then give us one of the representations of 164,762 as sum of two squares. The second thing to notice is that we can go backwards with the convergence. By applying the well-known cross-product formula involving numerators v and denominators u, we can trace the convergence in reverse order, from right to left. This approach effectively forms a chain of extended Euclidean algorithms. While this method does not offer a faster calculation of convergence, it provides an alternative perspective on continued fractions computations. In conclusion, Hermite's simple continued fraction method and Brillhart's Euclidean algorithm offer an exceptionally straightforward and fast approach to decomposing primes of the form 4k plus 1 into the sum of two squares. However, the rationale behind why they consistently yield the desired solution may not be immediately apparent to the untrained observer. On the other hand, the simple descent method, while lengthier and consequently slower in achieving the final result, excels in clarity at each step. By leveraging elementary symmetric polynomials, it becomes evident how divisibility is guaranteed throughout each descent. This approach not only ensures a systematic process, but also facilitates the presentation of the solution in a formulaic manner. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. If you haven't already, consider subscribing to my channel for more elementary number theory content. Stay tuned for future videos by hitting that notification bell so you never miss out. Your support means a lot.